let's go over what adapters are and some of the design principles behind them. So basically, as it says here, adapters, mechanical adapters, they hook two things together that don't have common interface. So one might have bolts and the other might have holes. And one might have a square surface, the other might have a round surface. Anytime where two parts won't just go right together, and they need to go right together, you need something to adapt them. So they're called adapters. Sometimes they're called couplers, sometimes they're called transitions. But basically, adapters is a good general term. And they need to be designed right because they will otherwise be a weak point in the design. And so when we do design them, since we have work to do, we're going to prioritize a few things. One is functionality, of course. It has to work. Two, strength. It's got to be strong enough. It is, every time there's a connection, that's considered one of the possible weak points in a design. And so we want to make sure it's strong enough. And then we want to make sure that there's ease of use. Can you put them together easily? And so those are the main things that we'll take a look at. So let's look at those in more detail. There's some principles that help us do that. One is ensure form and fit. Okay, form is like shape and fit is like size. This is not ensuring form and fit. Square peg in a round hole. You want to make sure that the shape is correct and the sizes are correct. You need to make sure, in essence, that no matter what, those two parts are going to go together. Okay, so that's ensure form and fit. Verify adequate strength and rigidity. We don't want things to fall apart and come apart as we hook them together. Okay, this is an adapter. It goes from one rod to another rod. Okay, it's called a rod end or a rod. And so we need to make sure that it's going to be strong enough and rigid enough to do the job that it's intended to do. And then we want it to be easy to use and easy to put together. Here's an example of one that is not. Okay, so those are like three big principles. Let's see what makes up each of those principles. First, we've got ensure form and fit. We should consider compatibility. Okay, are the parts compatible through this adapter? Okay, should seem like seamless connection. Should ensure proper alignment. So if I've got an adapter and it's maybe not parallel, one part is going to go twanking off into a different direction and things like that. So we want to eliminate gaps. We want to eliminate misalignments. Those things lead to performance problems, wear, tear, or just basically not fitting later on. And in lab, we'll talk about that a little bit more. Okay, so how do we do that? One good way are conformable materials. I will show you an example on the massage table about how they use, it's not actually an elastomer, it's a piece of cork that's a little bit springy. And we'll talk about, though, elastomers and spring washers and things that help things grab and take up for any misalignment. There is no way to make every part perfect, so there will be some misalignment, and we have to understand it. Another way is to use mechanical adjusters, either shims or jack screws. We know there's going to be a gap, so let's make something that will stiffen or harden that gap. And then the other way besides a mechanical method is gap filling adhesives. You can think of that as DevCon or some sort of epoxy that helps things stay in place. Of course, in our application, we want this to be removable. So this might be, gap filling adhesives might be a really bad option for us. Okay, the next thing about adapters for form and fit are clearance. Okay, sometimes there might be a little piece sticking out or a radius or something like that. And so we want some clearance for those parts. And I'll show you some examples of that. But you have to identify objects that are going to interfere, and then we have to cut clearance zones for those things. Okay, so that the parts that are supposed to mate can mate without running into another object. And then the other part of clearance is if I've got bolts and they're in a pattern, if I don't make that pattern perfect, or there's some little bit of misalignment, do I have clearance to still get those holes over the bolts? So clearance is a really big deal. And then, of course, material selection. We've got to pick something that will give us the strength and durability to do the job we want. If we're using metals, corrosion and thermal expansion are always of issue. And then wear and tear. Some things wear better than others. And as I've told you on this particular application, you might have thousands of operations for it to go through. So those are all things for form and fit. Let's look at the next part, adequate strength and rigidity. So there's load bearings. The adapter must be able to withstand the forces that will happen in operation. We're going to start looking at that a little bit, but that means you have to know the loads and the constraints. Okay? What parts are firmly fixed, what parts can move under load, things like that. And it needs to be a real analysis. Okay? And that's what we use finite element analysis for. We want to make sure that that analysis is true and good within our limits of understanding. And then we also have to know the significance of a failure. Okay? If the failure is just, something that's easy to see and something stops working, there's no danger, that's different than, say, somebody sitting on the piece of equipment and having it break away underneath them and falling and hurting them. So significance of the failure is important once you've seen the possible analysis failure modes. Stiffness is another one. So here's where we're going to be looking at safety factor. Stiffness is another one. If things move too much, you lose your alignment and maybe parts won't operate. So our material selection needs to be such that under the analysis, we also have proper stiffness. Now, nothing can have no movement. There's always going to be some deflection. But we're going to use our best analysis tools to minimize that deflection within reason. Okay? And so then we want to optimize that material. And that, for us, means optimizing the material size. Okay? Bigger is heavier, bigger is more expensive, bigger is in the way. So we want to optimize it. We want to get the smallest material to use, or maybe the one that fits within our cost zone and that still meets all these requirements. Okay, and that's where we can also look at thermal expansion and corrosion. We won't really have to work with thermal expansion much because we're going to operate at room temperature, but corrosion will certainly be one, especially if we're using types of bearings. And wear, as we lift things up and down and roll them and have gears go by, we want to make sure that we've done a good wear analysis too. So this is a lot, right? Adapters, there's a lot to these things. Don't expect you to be pros, but we expect you to understand that these things are all important, and you're going to touch on the ones that make sense. And finally, maximize ease of use in assembly. So simplicity is a big deal. Okay? Fewer the parts, the more simple the easier it is to operate in general. Not always, but often. Reduce the number of fasteners. The fewer things you have to put together and screw and crank together in general, it gives you a more simple, easier to use, easier to assemble design. And minimize the number of contact points. Usually you use 2 or 3 contact points because those will always go in and lay in without wobble. Okay, so simplicity is important. Standardization. Use only one tool if possible. Ease of use in assembly. And the other part of standardization, which isn't listed on here but is important, is use something that is normal. It's standard. It's been used over and over again, and you're sure it's going to do the job you intend to because it has a track record. Okay? So we don't want to make special fasteners, special threads, some weird type of connection that's never been done before. And above all, we want to keep it so there's only one tool. And if that one tool can be your hand, that's even better. Okay, accessibility. Make sure that you can get to it. I think you've all probably tried to put something together or do some sort of a job where there's just no room to do it. And it just makes people upset and nobody wants to do that. So one-handed assembly is good. It's the best. Two-handed for sure. If you need 3 or 4 hands to put this together, you're getting outside of ease of assembly. Should be able to do it from an upright position. If you have to lay down on your back or scrunch down and contort into a weird position, that violates ease of use in assembly. And the fewer parts and lower the weight in general, the easier it is. So that's sort of about adapters. We've got a lot of things to do and think about. Hopefully you'll review this before it's time to get down and do your concept work on it, because you got to be thinking about this. There's a lot to think. That's a lot of things to think about. This is why experience really helps. You may or may not have any experience, but you'll do the best you can. And that's the other thing about concept work is that you get to try it, and if it doesn't work, you fix it. So there's one last thing to look at is, we've talked about simplicity, different parts, standardized parts. Here's where you can get certain materials that might have the shape that you want already, and some sources for them, because that's also important. You want to know what's available. Sort of like that counterbore that I called out in my very first design that didn't exist, and the machinist was rightly upset. If I had known that there was a catalog full of counterbore tools, I could have called out the right one. So you want to, if you're using square tube, round tube, square bar, whatever, you want to be able to go and find it and know what the common sizes are, and even what those sizes actually are. Is 1.5 inch really 1.5 inch, or is it something slightly less or slightly more, or have some variation? Is it straight? Things like that. So I've just picked some. These may not be what you end up using, but you can see the types of keywords that are available for the searches and at Metal Depot, Fastenal, Granger's, things like that. And so if I haven't shown you exactly the one you're going to use, you can get online and find it. So as an example, in my samples I'm going to show you, I'm using wood, maple, because it's readily available, and I think it might be strong enough, and I know that I can woodwork it very, very easily, and then it'll match sort of the table. That's not necessarily something that's important, but I'm doing it just also to show that I have to go look up materials sometimes. So there we go. That's sort of an overview about adapters and the design principles that we're going to follow. So please look this over, study it, and then apply it during our work on adapters this week.